In this video, I'm going to talk about velocity versus time graphs. And I want to start over here with a position versus time graph and sort of show how we go from that into the velocity versus time realm. So I've got something here. The position versus time shows where it is at any given time. And the statistic that we need from that is the slope, which is the velocity. If you think of this section right in here, the position isn't changing very much, even though time's passing. So that's going to be slow. Over here, the position over here is changing quite a bit in just a short amount of time. So it's going to have a higher velocity. So that slope, the slope of that line, ends up being the velocity. And I know it's curving, so it's not just one slope. So you actually have to take the tangent to figure out the tangent line to figure out the slope of the part that we're talking about, and I'll show you how that works. Now, when we're doing these things, I always like to be able to look at these from multiple angles. First, we want to be able to, here, what we've got here is a graph. We want to be able to describe the motion, we want to be able to draw the motion, and we want to be able to represent the motion with the equation. And I've got this down here so we can do a motion map, show how the dots go, how that motion goes, where they're far apart. A motion map is sort of like a strobe light picture. So let's look at what happens here. I said here that it starts out, it's essentially flat. If I draw a tangent line to this part right here from 0 to about, a little less than 1, it looks like the slope is 0. So when we come over here in the velocity versus time graph, that means it's going to be a very small velocity. Let's say it starts at 0. If we come over here and we draw a tangent line at this spot, let's say at 4 seconds, looks like it's about as steep as it'll ever be, and we draw a tangent line there, then what we find is the slope of that is it goes up 100 meters and it goes over 5 seconds. So there, slope 100 meters per 5 seconds. So that's a velocity, sorry, I'm trashing the joint, a velocity of 20. And what I want to do with this is I'm going to assume that this is speeding up at a constant rate. If you're in AP Physics C, that's not always true, but I'll say it's speeding up at a constant rate. Okay, so the slope continually gets bigger up to 4 seconds. But then something happens. There's a point in here where it stops getting steeper and steeper and it starts getting shallower and shallower. And finally, at the end of 10 seconds, the slope of that part is 0. So we know at 10 seconds it's 0. And it gets less and less, and I could go through and do some sample slopes, but once again, I'm going to assume that it slows down linearly and comes to a stop or a 0 velocity instantaneously, meaning only at 10 seconds is that slope really 0. A little beyond, it starts to get a negative slope, and let me draw that. So over here at 12 seconds, it's got a negative slope. I'm just going to assume that it keeps going linearly, and something like, something like this. I should have a ruler here, but I'm being very lazy. So this captures it. It gets steeper and steeper at 4 seconds. It's quite steep. It's moving pretty quickly in the positive direction, positive slope. Then it's getting shallower and shallower until at 10 seconds it has no slope, 0. Then it starts to get a negative slope. Now, if we look at the velocity versus time graph, we can see faster, faster, faster in the positive direction. A lot of people think this means it's moving in the negative direction. It's not. It still has a positive direction. Let's look at exactly 7 seconds. At 7 seconds, it has a velocity right around 10 meters per second, but positive 10. Negative 10 would be down here. So anything up here is moving in positive direction. Anything below that time axis means it has a negative velocity. It's moving in the negative direction. Now, there's a skill. Every time you look at a graph of any sort and trying to interpret it, take some key points. If I were given this, I would say, okay, it starts at a velocity of 0, increases to a velocity of 20, increases at a constant rate, then decreases at a constant rate to 0, and then beyond that to some negative number down here. At this point, during that part, it's going in a negative direction. We can actually go back in the other direction. The slope of the position versus time allows us to find the velocity versus time graph. And in a second, I'm going to show you how you can take a velocity versus time graph and get at least some information about the position versus time graph. But first, let me come back here. I said we were going to do the motion map, and I want to take a look at that. So here, at 0 seconds, it starts out at position 0. And then let's just do it every second. Here, it moved to, I don't know, maybe 5 meters. After 2 seconds, it's probably about, I don't know, 12 or something meters away from the origin. After 3 seconds, somewhere around 22. 4 seconds, it's 40. 5 seconds, I'm going to say 57, 58. 6 seconds, about 70. 8 seconds, about 90. Something seems wrong there. Let's see. 6 seconds, I'm sorry, it was 70. 7 seconds, 82. 8 seconds, 90. And at 10 seconds, well, I'm sorry, 9 seconds, a little less than 100. 10 seconds, 100. Then it starts moving back in the other direction. 11 seconds, maybe back like this. 12 seconds, maybe 96, something like that. So it moves in this direction, then comes back. Those are the positions. And you can see getting farther apart, so faster and faster and faster, slower, 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 then speeding up in the other direction. The velocity vectors are going to be proportional to the displacements, since they're all constant time. So you can see the velocities getting bigger, bigger, smaller, smaller, but still positive, smaller, smaller, and then going back in the other direction. And that's consistent also with this graph. Bigger and bigger and bigger velocities, smaller and smaller velocities, and then velocities in the negative direction. Okay, now I want to show you how we could go from a velocity versus time graph to some information about the position versus time graph. Slope of position versus time gives you velocity. It turns out a thing called area under the curve, and let me adjust here. Area under the curve gives you the position information, but really more to the point, the displacement information. So I'm going to write it over here. Area under velocity versus time curve. And this is just an expression we use, area under the curve. It really means area between the graph and time axis. And then we count above, any area above the time axis as positive, below as negative. So we use the area of the velocity versus time curve, the area between the graph and the time axis, counting above as positive and below as negative, to determine displacement, delta x. I'll give you an example. If we have an object traveling at a constant velocity, here's the velocity in meters per second. Here's the time. in seconds. And let's say 0, 10, 20 meters per second. 2, 4, 6, 8. I almost never have 1 as a unit just because I want to make sure we get away from counting squares. Let's say it's going 20 meters per second for 8 seconds. If we write the equation for the velocity, average velocity, displacement over time, 20 meters per second equals the displacement over 8 seconds. We multiply both sides by 8 seconds. This side cancels out. You have delta x equals 8 seconds times 20 meters per second. Seconds divided by seconds, those cancel. So you end up with delta x is 160 meters is the displacement. So that's just using the equation. And again, being able to represent with an equation or draw. We could do a motion map, although it's really dull because they're all equally spaced. It's a constant velocity. And the graph of velocity versus time. Now, to find displacement, I said displacement is the area under the velocity versus time graph. Well, think of this. We'll think of it like this. 20 meters per second. If it goes 20 meters per second for 1 second, it would be travel 20 meters. 20 meters per second for 2 seconds, it would be 40. So you can sort of see intuitively how this area under the graph, in other words, the area between that and the time axis, represents how far it went. The displacement, delta x, is going to be the area of that rectangle. 8 times 20, hey, guess what? Ends up being 160 meters. 8 seconds times 20 meters per second, just like our equation here. And that looks pretty trivial, except then what happens is we could now, it gives us some power to do this. To do, let's say it's a changing velocity. Okay, let's take that same scale, 20, 10, 0, and the time scale, 2, 4, 6, 8. Now it's changing. We can't use that equation, average velocity equals delta x over t. Well, we can, and I'll talk about that in a second. But let's just, to do it like this, we don't have average velocity or constant velocity. So what we can do is we can say, okay, it's the area under the curve I mentioned. So it's the area between that graph from 0 to 8 seconds and the time axis. What we can do is we can break this into, we could do it as a trapezoid, but we can break this into simpler sections. That's a rectangle and a triangle. The area of the rectangle, just like before, is 160 meters. It's not 8 squares. We don't care about squares. We care about physical measurements. 20 meters per second is the height, 8 seconds is the base. We have 160 meters. This triangle is 1/2 times the base is 8 times the height, which is 10. The height of the triangle is 30 minus 20 times 10 equals 40 meters. So the total displacement is the area under this curve, the whole of that. 160 plus 40 is 200 meters. And let me come over here. I mentioned, well, let's actually, no, I'm going to go here. Now let's look at, I mentioned that counting below the time axis is negative. So let's do this. I'm going to throw a ball upward with a velocity of 4 meters per second. This is my velocity. 2, 0, -2, -4 meters per second. And let's see, I'm going to do tenths of a second here. 0.1, 0.2, well, let's do 0.2, 0.4, 0.6, 0.8. And this is the graph of how that ball would behave. And I'm going to call up positive. So I throw a ball up. It leaves my hand going 4 meters per second. And then it comes back down, and it's going negative 4 meters per second after some time. So it slows down, slows down, slows down, stops up at the top, speeds up, speeds up, speeds up, speeds up. And we haven't really talked about freefall, but this would be the graph for freefall. This is how balls actually go up in the air and come back down. This is the, I know the slope of this because I know something about the acceleration, which we'll talk about in the next unit. So if I look at the area under the curve, look, a lot of people make the mistake of saying, oh, it's got to be under that whole curve. No, it's the area between the graph and the time axis. Well, up to 0.4 seconds, that is the area between the graph and the time axis. From 0.4 to 0.8 seconds, this is the area. And I'm going to count this as a positive area and this is a negative area. And this ends up being area is 1/2 times 0.4 times 4 equals 0.8 meters. Whoa, a disaster there. So this, during the time until it gets to the top, it went 0.8 meters. It went up 0.8 meters, and I can tell this is the top because that's when it stops going up, stops having a positive velocity and starts getting a negative velocity, starts coming back down again. This one has the same size. 1/2 times 0.4 times 4 equals 0.8 meters, but it's in the negative direction. We count it as a negative. The absolute value, usually when we take area of anything, you never have a negative area, but we count this, since it's below the time axis, it's negative 0.8. Plus 0.8 minus 0.8, total displacement is 0 meters. And that's what happens when you throw a ball up. It's a symmetric problem. When it has that same velocity down, it's back at your hand. It's come back down. Okay, so I think this gives an idea of how we use position versus time graphs to find velocity versus time graphs, and how we use the area under the curve to find the displacement.